Hello, my name is Ricardo Matheus, and I'm a professor at the Institute for Theoretical Physics in São Paulo, also known as IFT. This is the very first video in a second series of videos on quantum field theory. It comprises what I like to call the course Quantum Field Theory II. Of course, if you look around, you see that Quantum Field Theory II courses are very different in different institutions and different professors. Right? But we'll cover, firstly, right, the very first part of the course, we'll cover one of the subjects that is always covered in Quantum Field Theory 2, which is renormalization. So in this very first video, I want to motivate the need for renormalization, or at least raise the questions that lead to renormalization. As far as the technology goes, I'm testing with background removal. As you can see, the results are not very good. Maybe I'll have to buy a green screen. But since my face will be for the happiness of all, always small in the picture, I hope this badly cut thing won't bother you. So let's get down to business. We start with this one slide review on how we work with quantum field theories. So if you're trying to model a system with a quantum field theory, the very first decisions you have to make are about two things, right? On one side, you have to decide on the degrees of freedom you'll be using to describe that system, right? Essentially, how many fields you're putting in, right? And also, you have to decide on symmetries. And of course, how these fields will transform under the symmetries that you think your system respects, right? These two things are closely linked, right? And together, they will define a Lagrangian density, right? Which contains the information on your model, right? This is essentially you modeling the system. Then, once you have written this Lagrangian, right, you have a theory, right? Quantum field theory, which we have found to be the one consistent theory which is relativistic and quantum at the same time, right, as we have seen in quantum field theory 1. Right? Once you plug this Lagrangian inside the quantum field theory, which describes a series of procedures you have to do to link these Lagrangians to observables, right, you will obtain a number of things, right? So you could get equations of motion, right? You could get elements of the scattering matrix, the S matrix, right? You can get conserved quantities, so it's pretty easy to calculate processes and show which processes are forbidden because they will violate some quantity linked, of course, to the symmetries of your model. And you could, in principle, too, while it's not easy thing to do, you could, in principle, calculate bound states, right? In other words, the quantum field theory gives you a way, departing from this Lagrangian, which, of course, is based on these two assumptions above, right? Leads to testable consequences, right? So you have a number of testable consequences from those hypotheses you started from. Let's then refresh our minds on this whole business of choosing symmetries and degrees of freedom. Of course, the main symmetry that plays a big role here is that of the Poincar group, right, which comprises both rotations and translations in four-dimensional Minkowski space. Right? That's the one big assumption we put on quantum field theories right from the start, right? And so when we're choosing fields, we'll go for representations of that group of transformations. Right? So if you do a Lorentz transformation, for instance, which is part of the Poincar group, and your space-time coordinates transform like this, right? your field will also suffer a transformation, right? Which can be generically described in this way. I can associate some index to your field variables. Let's assume it's more than one. It could be just a simple field, just one number, but it could be more complicated than that, and that's what this index indicates, right? And this is the form of the field in the new coordinates, right? And it relates, generically speaking, to the form of the field in the old coordinates. So not only the coordinates change, but also the functional form of the field. Sorry, this is J, right? And different choices for this representation are here, right? Which is a representation of that transformation over there, right? Lead to different properties for this field. So we have many examples, right? So the simplest choice I could make for R, right, of course, is the identity, which then implies that phi prime x prime is equal to phi x, right? And this, as we have seen, is a scalar field and leads to bosonic excitations of spin 0, right? On the other side, we could choose R to be equal to the Lorentz transformation itself, right? And that would lead to fields where this index is actually a Lorentz index, right? So let's go this A mu prime x prime is equal to lambda mu nu A nu x. So these fields, for this choice, they transform as vectors under Lorentz transformations. And we, of course, we have seen that's also a bosonic field, right? That represents particles with spin 1. Right? We could also go to more complicated representations, like this one, right? Remember these MD, we have seen these all. Right? If you didn't, please go look at the quantum field theory 1 videos, right? But this is defined as theta mu nu S mu nu. This is just numbers, and S mu nu is a 4x4 matrix given by this commutator of the Dirac matrices. Right? So fields that transform under this particular representation, right, they will have also an index that goes from 1 to 4. Let's call this alpha. Right? Alpha goes from 1 to 4 is not a Lorentz index that transforms under this matrix, right? And these guys will transform like that. MD, of course, this has two indexes, alpha, beta, right? Psi, beta, x. And we have seen these leads to fermions with spin half, right? So you see that the choice of symmetry, in this case, Poincar invariance under the Poincar group of transformation, right? And the choice of representations of the fields tell a lot of what kind of system I would describe. I'm talking about the properties of the particles, which will be excitations on these fields, right? And of course, also I have to know the number of particles. So if I want to model QED, right, electrodynamics with just the electron, right, I could take one psi, just one of these fermionic fields for the electron, and another one of the spin 1 fields that would produce the photon, right? That would be enough. But if I want also to describe a system when muons are playing a role, then I need two fermionic fields, one to represent the electron, one to produce the muon, right? And just the photon to communicate both of these fields and create electromagnetism, right? So I'm not only modeling symmetries, but also content, matter content, right? And of course, that's not the only symmetry. You have other internal symmetries. Let's see a few examples. take nuclear physics, for instance, right? At the scales involved in the nucleus, right? The strong nuclear interaction is so much stronger than electromagnetism that you can basically consider the proton and the neutron like two states of the same particle, right? Their masses are similar, and if you can disregard the electromagnetic interaction, then their charge doesn't matter. That means you can define a nucleon field which has two states. One of these states being the proton, and another one being the neutron, right? This field, right, will transform under a SU2 symmetry that we called isospin, right? And it's a global symmetry. And as you probably know, it was very useful in describing nuclear interactions, right? And these two fields are transforming under the fundamental representation of this global symmetry. And that fixes a lot of their properties. Also, if you want to describe the interaction between protons and neutrons, you have to introduce another field, which is the pion, right? And the pion also needs to transform under some representation of this SU2 global symmetry, but it's not the fundamental one, because we know the pion has three states now: pi plus, pi 0, and pi minus, right? Which is the adjoint representation of this SU2 global symmetry. So you see these two are both the existence of the symmetry and the way the basic fields in your theory transform under it will fix a lot of the properties and what kind of Lagrangian can you write out of these fields. And we have found that this choice in particular is very good to describe nuclear physics, right? Let's see another one. So one way you could obtain QED, right, is assuming, okay, we have an electron in nature, right, which is a spin half particle with charge. So there is some conserved quantity beyond those from the Poincar group, right? And we, for some reason, I don't want to get into right now, decided to make that symmetry that creates the conserved surge a local symmetry, which means the transformation can depend on the point you are in space-time, right? So the assumption we're making here is there's a field of spin half for the electron, so it transforms like a spinor under Lorentz transformation. So I'm introducing a spinor. But I'm also demanding that the U1 symmetry that could create the conserved charge of the electron is a local one, right? So this field, instead of transforming like this is the charge, this is exponential, right? Be careful. Instead of this being just a number, it's actually a function of position, right, in space-time. When I do that, I made this local U1 symmetry, right? And if I try to write a Lagrangian that is invariant under this local U1, I'll find I have to introduce a spin 1 field too, right? Which, as we have seen above, is a vector under Lorentz transformations, but transforms like these under this U1 under this local U1 transformation. With these two fields, I can only write the following Lagrangian. This is the covariant derivative, which makes this invariant under local U1. And this is a kinetic term for this field. Again, I won't define these things because I'm assuming you have seen this before, right? Just to make it a little bit more explicit, right? The covariant derivative right? Is just the normal derivative plus this term, which gives the interaction between the electron and the photon. Right? And this describes very well quantum electrodynamics. You could take a very similar approach for quarks. Right? You could take a quark, one quark, say the up quark, right? And do the same for color, right? There's just this symmetry, which is SU3 in the case of color, and make it local. They would force you to introduce, again, a gauge field, that's how we call these guys, right? Which is the gluon, ends up being the gluon, right? That's not the only way to get to these gauge symmetries. In fact, you could start from the photon and say, well, I have a spin 1 photon which is massless, right? What kind of consistent theory can I build for this guy? Right? And consistent, we'll dwell on what consistent means when we go into renormalization. But turns out that you also have to enforce this local symmetry in order to get a consistent symmetry for spin 1 particles, massless or massive, right? So again, the message I want to pass right now is that these, or at least remind you of, right, is the interplay between the amount of particles you want to describe and symmetries, which plays a role in writing these Lagrangians, of course. Now, once you have these Lagrangians, you can go forward and get to observables. So here we have like this very schematic way in which you can get scattering amplitudes, right? So using those three definitions right there, you can get the matrix element, this guy right here, and plug it into a formula for the scattering cross-section, right? Of course, the way to get from the Lagrangian to these S matrix elements defined here is one of the things we want to look closer now, right? But the main point is that at least 3 level, at the very first approximation in the perturbation theory, we know how to do that, right? And the main point is that in quantum field theory 1 course, usually, and in our case that is true, you only do that at this very rough first approximation, right? You just take the perturbative expansion and all you see about this guy is the very first contribution, right? Which we call 3 level, leading order approximation, first order in perturbation theory, right? And of course, if you just think that, okay, now we go to the next order, and all that happens is a small numerical correction to the numbers we calculated at 3 level, right? There probably wouldn't be a whole course about going to the next 2 leading orders. So we'll have some very striking new effects when we go to the next 2 leading order, and that's one of the things we want to stress, right? There's a lot of conclusions that we draw in quantum field theory 1 were based on the 3 level approximation of the theory, right? And now we want to go back and look at these conclusions and see how solid they were and what kind of changes and new effects show up when we go to the next one. There were, in fact, already a few hints that we were not looking at the whole picture, just staying at leading order when we worked in quantum field theory 1. So any attentive student could have asked at any moment when we were doing that business of writing Lagrangians, take again, for instance, the electromagnetism 1, for 1 electron and 1 photon, right? Just the same I just wrote before, right? Any attentive student could have asked at this point, right? Where are the other terms, right? If I only demanding that this is the most general Lagrangian, that is invariant under the Poincar group transformations and that local U1, right? Why didn't I write, for instance, a term like this one, say some constant, right? And psi bar electron, psi electron, psi bar electron, psi electron. If this mass term here is invariant under everything, this is also invariant, this is also invariant under all the symmetries I'm proposing. So this is a totally valid term, right? Same goes for C2, say another constant, right? F min u square, which is just the square of this one, right? Or this one cubed and so on and so forth, right? Same thing here. I could put another psi bar, psi, I could mix psi by psi with F min u. I mean, there's literally an infinite number of other operators I could write here, right? So you could ask very rightfully, right? Where the hell, right? Where are these terms, right? The answer to this question is very closely related to another question, right? So take again this Lagrangian. Let me just move it over here, right? There's a bunch of conclusions I take from here. Let me explicit the interaction now again, right? So I have an extra minus I E a slash psi bar psi, right, electron. Right? And just by looking at this Lagrangian, we have a bunch of conclusions, right? That we learn how to read these Lagrangians in quantum field theory 1. So again, I can read from it. There will be an excitation in the spectrum of this theory. It will contain an excitation. There is an electron, right? Also a positron, right? Because I know this is a complex field, there will be antiparticles, etc., right? I also know, just by looking here, but we figure this out in quantum field theory, there will be a photon. So another conclusion I take from here is that there is an excitation with spin 1, which is massless, etc., right? And there's more. Just looking here, I say this is the mass of the electron, right? Also, the mass of the photon is 0. There's no mass term for the photon anywhere, right? Also, this is the coupling between these two guys. And this is a coupling that is just a number here. It doesn't depend on momenta or anything, right? All this, it's important to keep in mind that all these conclusions were drawn at tree level, right? I just did calculations at very leading order for these fields. And that's where all these interpretations of these numbers and fields in the Lagrangian come from, right? And the whole point of having a whole course to deal with the next to leading order or loop corrections to quantum field theory is that a lot of these conclusions don't hold up, at least not exactly, right? And they are especially tricky if you're not talking about weakly coupled theory. So keep in mind, all these conclusions were drawn at perturbation theory. That means I'm looking at a weakly coupled theory, and even being weakly coupled, I'm looking only at the very first contribution from that interaction right there. Right? Now, of course, not everything is lost, right? If all these conclusions flew out of the window just by going to next to leading order, then the quantum field theory, of course, would be useless, right? What we'll see is that as far as the quantum, as far as the degrees of freedom go, we're very close to target, right? So we won't find a theory that has no electrons or no photons anywhere, right? Of course, that depends on energy scales, but we'll get to that. But we are very close to target as far as the degrees of freedom go. As far as these constants that we have identified as the mass of the electron here or the coupling, that's trickier, right? They will receive considerable corrections, right? But as far as weakly coupled theories go, we know how to calculate and incorporate these corrections and define masses that make sense. There are physical masses and physical couplings. But that will imply I have to change this Lagrangian. If I want the physical mass and the physical coupling to show up in the Lagrangian, this Lagrangian will not be the right one, right? But we'll learn how to calculate the new Lagrangian, right? But we'll calculate the new Lagrangian from this one. And that's the important part of this whole process, right? The information is contained here. It's not explicit at all levels in perturbation theory, but it is contained here. And that's the main point of this course, is to learn exactly how information is encoded in these Lagrangians, right? And of course, the things get way more complicated when you go to strongly coupled theories, right? We could write a Lagrangian which is very similar to this one for quarks and gluons. There's a few changes you have to make because it's a non-abelian gauge symmetry instead of an abelian one, which you have here. But it's very similar. The situation is very similar. But we know that for quarks and gluons, if you go to low energy, right, compared to mass of the proton, for instance, right, this theory is not only strongly coupled, right, it's non-perturbative, and we know there's no quarks and gluons to be seen anywhere, right? They are not seen at low energies. All you see is hadrons, right? You see protons, you see neutrons, you see pions, kaons, you name it, right? So even this one-to-one relation between particles and the physical resonance, the physical states you see, is lost if you go to strongly coupled theories. And you have to be careful about that. Of course, quantum field theory has to incorporate that somehow, because again, the information is there, right? And we have to learn how this information is encoded, right? If you would have to summarize what studying renormalization teaches you, right? I would summarize it this way, right? Renormalization is a procedure that makes much more clear how physical information is encoded in these Lagrangians. It's not and this information is not encoded in the very simple way that it is at tree level, if you stop your conclusions at tree level. Right? So that's the very first we'll be looking at, right? Is starting with the next video. So see you soon.